Okay, so I'm sorry, actually there is a power problem here, so my backup didn't work. So let me just quickly, I think we discussed about the expression binary tree, so I will not repeat this. So let's discuss a new topic, which is basically like what is the uniqueness in binary trees, right? So we will try to understand that. So I'll show you two trees here. Please work out on your chat box and see what is the in-order traversal of these trees. Please share your answer in the chat box. Right. So you are saying BA, DCE, right? So this is correct. So what is the observation? For these two binary trees, these are not same binary trees, but they have the same in-order traversal, right? And now I'm showing you two other trees. What is the pre-order traversal for both of them? Just try out in your chat box. Right. So your answers are correct. So I hope you are comfortable with the traversals. Now you can see again the bottom two trees which I am showing on the screen. These are two different binary trees. They are not same. But pre-order traversal is same for both. So the question which I am trying to raise is, given a traversal, okay, for example, if I give you a traversal, there could be definitely more than one binary tree possible, right? We have seen just now. So how do we call, like, let me put it in the right way, how many traversals I need, right? Say for example, how do I fix, okay, if I give you an in-order traversal, if I give you a pre-order traversal, whether both of them they belong to a unique binary tree, or even in that case it is a possibility that even those two traversals are possible for more than one binary tree. Okay, so this is a question which I am raising. Okay, so normally what happens, you need at least two traversals, okay, in-order traversal and one more and maybe some other condition to define a unique binary tree. Okay, this is a requirement, and then I have few questions related to that. We will see. So the point which I am trying to bring forth is that you need two traversals and some condition to define a binary tree uniquely. So for example, if I give you only one traversal, then it is a possibility that they belong to more than one tree, which we have seen on this screen just a few minutes back, right? But if I give you two traversals, then it is not possible that they belong to two different binary trees, right? They will define a binary tree uniquely. So this is the point which I am talking about. Now, what actually, like some of you, as you mentioned, like, okay, in order, yeah, in order is a requirement, that is correct. Now, if I see, like, if I give you two traversals, whether you can construct a tree, yeah, this is possible, right? So let's do an exercise here in the class to construct a binary tree when in-order traversal is given and pre-order traversal is given, right? So we will attempt to make a unique binary tree out of it, and as you see, like, in-order traversal is given, so definitely this is going to define a unique binary tree. As I mentioned in the beginning, in-order traversal, the root will come somewhere in the middle, right? And in the pre-order traversal, the root will be in the beginning, right? So which I have highlighted that root is definitely going to be A, and that is also highlighted in red color. Okay, so that is an open secret which we can make out in just by looking at the traversals, right? So with no doubt, I can actually construct my stage 1 tree in the given form which is shown on the screen. A is definitely going to be the root because that is the first node in the pre-order, and its left child will be DGB, right? Why is it so? Because DGB is occurring on the left side of A in the in order, right? And in the right side, HEICF. The rest of the elements will be occurring on the right side. Now, the things are very simple at this stage, but as we move forward, probably the complexity will increase, right? Now, let us try to expand the left subtree, which is DGB. So, how do we go about this? Who's the root of DGB? DGB is definitely going to construct a subtree, but who's going to be the root? So, what is your answer? I mean, if you use the same logic, what will be your answer? Right. So, some of you are answering it right. If we see pre-order, my B node is coming immediately after A. So definitely B is going to be the root of the left subtree of A. Okay. Fine. So I can make actually B as a second node or the child of A. But what about DG? DG will come on the left or right. What will be the arrangement of D and G? What is your answer? Yeah, so some of you are saying it correct. Since if you see in order traversal, D, G, both of them are coming on the left of B. So it means what? That D, G are left child of B, right? So my second iteration to construct this tree will look like this. Okay, please convince yourself. I know DGB belongs to the left side of A, right? Because in the in order DGB, all these three nodes are coming left of A, right? Now, who will be the immediate child of A? It will be B, because B is the second node after A in pre-order traversal. Alright, so I lock down B's position. But what about D and G? D and G are occurring on the left side of B, right, in order traversal. So I am sure that DG are left child of B. So that is the reason the second tree which I am showing, DG are occurring on the left side of B. Now how do I expand D and G further? If I see pre-order, I see D is the third node immediately after B. So for this subtree, the root will be D, right? D for dog. But what is the relationship between D and G? We see that if I make D as a root, no issues there, but G is occurring on the right side of D, right? So it means what? The next node will be D and G will be its right child. So how this tree will look like? This tree will look like as the third tree which I am showing on the screen at this point of time, right? So if you see for node A, my left subtree is completely taken care of. Now if I see my right cluster, which is HEICF, I can use the same logic, but let's see how does it expand. Let's go further. So my first step is I need to know who's going to be the root of this subtree. So if I see my pre-order, A is taken care of, B is taken care of, D is taken care of, G is taken care of, and the immediately after G, my next node is C, right? So definitely C is going to be the root of this subtree. Okay, so I have almost finalized the location of node C. But if I take C and I compare rest of the elements in the in order traversal, I see H, E, I are occurring on the left side of C and F is coming on the right side of C. So what does it mean? That C will be the root of the subtree, HEI will be on the left side, F will be on the right side. So my next iteration is going to look like as the fourth tree which I am showing on my screen. Alright. Now I am almost done except the cluster HEI. So how do I expand this HEI, right? So again, pre-order is going to help me out here. A is taken care of, B is taken care of, D is taken care of, G is taken care of, C is taken care of, E is not taken care of yet. It is a part of a cluster, it is not a single node. So obviously, E is going to be the root of this subtree. Okay. And what is the relationship among HEI? If I see E in the in order, H and I, right? Sorry, where is that? E. So if I take E, H is occurring on the left of E and I is occurring on the right of E. Okay, so E will be the root, H will be its left child and I will be its right child. Right? So the fifth tree which is shown on your screen on the bottom is the final tree expanding using this method. Right? And if you try it out, okay, you cannot construct any other tree. The procedure remains same more or less. So for example, I give you in order traversal and I give you post order traversal. So post order traversal, the unique property is that the root will be the last node, right? So you need to start back from the back side. Okay, here you started from the left side onward in the pre-order. Post order you need to start it from the other end. Okay. Now again, as usual, like there are a couple of exercises for you to practice. So the very first exercise is actually a YouTube video, okay, which is a very old video and which is still considered a classic example. Like if two traversals are given, how to construct a unique tree. There is an error in the video, okay, by mistake the instructor actually constructed a wrong tree slightly, but it is worth watching. Okay, so I would recommend you actually please do watch this. It will again clarify your doubts. And then there are a couple of exercises which expression trees are given. You need to construct the tree, you need to take the traversals, things like that. Okay. Fourth question is important. Okay, we did not discuss it in detail here. Do we think that in order traversal is a prerequisite? So for example, if I give you two traversals and I ask you like whether they are going to make a unique binary tree, so one of those traversals must be in order. Is it requirement or is it just like any two traversals will define a unique tree? Okay, this is something which I would suggest you actually draw few trees and convince yourself, okay, and then come up with an answer and let us discuss it on the forum. Why is it so? If you think, and if you don't think like that, what are the reasons? I mean, is it possible like if I give you only post and pre, you can still construct a unique binary tree? There is no other possibility for a second or a third tree. Okay, fourth question demands some thinking. Okay, come back on it. Now, so we have seen like trees, binary trees, properties, operations, and couple of other things on the binary trees. Now I have come to a situation where we can see some applications, right? Like how these trees are going to be utilized. Okay, so to use binary trees into applications, I'm going to use few other types of binary trees which you will see like they are built with certain properties. Okay, they are binary trees, but they are built with certain properties. Okay, some of the binary tree properties which are applicable globally we have already reviewed, but there are a few additional properties. If they are present in those binary trees, we name them differently. Okay, so this is what we are going to see now. So first one is heap. Okay, so heap is a very generic word which you might have seen at several places. Heap means a pile, right? Okay, which is basically a group of something. Okay, like a heap of garbage, right? Or so there are, or heap you have seen in the memory layout of a running program also, like where we, when we do malloc or calloc, the runtime allocation takes place, right? But when we say heap in a binary tree context, okay, this has a slightly different meaning. So what is it? Let's understand it first. So first of all, let's say what is a max tree. Okay, so please don't get confused that okay, I'm talking about a binary tree, then I'm talking about heap, and then I'm talking about max tree. These definitions are actually interjoined, so please bear with me. A max tree is a tree in which the key value, basically the value of the node in each node, is no smaller than the key value in its children. Okay, so this type of tree will be called a max tree. Max tree means, so if you have a root and there are two children of it, the key value of this root will be either equal to or bigger than its children. Okay, that's a simplest, I would say, like the most simple explanation I can give it to you, right? So then what is a max heap? Max heap, there are two conditions. One condition is that it has to be a max tree, okay, and it has to be a complete binary tree. Now complete binary tree we have reviewed last week, right? What is a complete binary tree? So if any binary tree meets these two conditions, right, which is mentioned on your screen, then we are going to say that this binary tree is a max heap. So let's quickly review it again. Max tree is where the parent value will be equal to or bigger than its children. Okay, simple language. And what is a complete binary tree? If you recollect last week's class, all the levels are completely full. Exception could be the last level, where the nodes will start filling from left side onwards. So that is a complete binary tree. And if we have these two properties, complete binary tree as well as max tree, then it makes a max heap. Similarly, I can define min tree and min heap. What is min tree? Where the parent value is equal to or less. Okay, not equal to. It should be less than its children's value, right? And it should be a complete binary tree. Then we are going to call it as a min tree and min heap correspondingly. So we will see the logic is same. It's only the question of equal or bigger or smaller. Okay, and complete binary tree is anyway a mandatory condition for a binary tree to be qualified to be called as a heap. So this is anyway a mandatory condition. So now you see a tree on your screen. Can you tell me like what is it? Please answer on your chat box. Yeah, so there are two things which you need to check. First thing is that every parent is equal to or larger than its children. So 9 is bigger than 8 and 7, fine. 8 is bigger than 6, fine. There are no other nodes. But is it a complete tree? Yes, this is a complete tree because all the levels are full except the last level where the nodes are starting from the left end. So this is a max heap. We can confidently declare it as a max heap. What about the tree which is now shown on your screen? So if I see, first of all, First thing actually what I would suggest you to check whether it's a complete binary tree or not. All the labels are full, and on the last label nodes are starting from left side onward. So this is a complete binary tree, no doubt about it. Now every parent is smaller than its children. This condition is met, so it's a min heap. It's a min tree and it's a complete binary tree, so it's a min heap, no issues. Okay, so on the last slide, completeness is a very important criteria. Please don't forget. I mean, just don't simply compare the numerical values or alphabetic values and declare it. Right? So some of you are saying like these are not complete binary tree and things like that, but I would say like, okay, please review your concepts. These are complete binary trees as per the terminology which we are following in our sessions. Okay, so now let's see a couple of other examples. What kind of tree is this now? Is it a, yeah, so this is not a complete. So I mean, the question of a heap comes later. First of all, this tree itself, it's not complete itself, right? So this is not a complete. So we cannot go and declare it any type of heap. Okay, so some of you are answering like it's a binary tree. So we have come to the later stages of binary tree when we are seeing more application. So simply saying binary tree will not be sufficient here. What about the second tree, green color tree, which is shown on your screen? Right. So you can see like it's a complete binary tree, no doubt about it. But min-max property is violating at a couple of places, right? So it is actually this is not a heap, okay, but it is a complete binary tree. What about the third tree which is shown on your screen? Right. So if you can, it's actually pretty simple, right? This is not a binary tree itself, right? So question of completeness or question of min-max comes later. First of all, this is not a binary tree also. What about the tree shown on your screen in blue color? Right. So if you see the blue color tree, this is not complete itself, right? Because if you see level 1, that is not complete. There is no right child of 9, right? So it is not complete. What about the tree which is shown on the screen in purple color? Right. So this is min heap. The reason is very simple because as we can see, it's a complete tree. All the labels are full except the last label where the nodes are starting from the left, and min property is satisfied. Every parent is smaller than its children, so it is a min heap. What about the tree which is shown in yellow color on your screen? Right. So some of the answers are correct, but some of the answers are wrong. So I think if there is still confusion like what is a complete binary tree and all that. So I would ask you actually to review that carefully and stick to that terminology. So here this tree is not complete. The reason is level 1 is full, level 2 is full, level 3 is not full, which is acceptable, but actually the nodes are not starting from left side onwards. Okay. Why is it so? Because right child of 5 is not present. If I make 2 as a right child of 5, then it will be a complete tree. So there is a vacancy, right? 5 doesn't have a right child, there is a vacancy. Before filling up that vacancy, I am filling up the vacancy for 6. So that violates the property of completeness. Okay, so first of all, it is not a complete tree, so let's not discuss about whether it is max tree or min tree. Okay. Now, what I would do actually, which is important for you for your mid-semester evaluation also, please pay attention to this type of question. I'm giving you a few integers, okay, in a random order. And now you need to construct a max heap out of these numbers in the order of their occurrence. Okay, in the order of their occurrence means 0 is coming first, 14 is coming next, -4 is coming next, then 87 and 86. So you need to take one integer at a time, okay, and you need to construct a heap. What type of heap? A max heap, taking one integer at a time from left to right. Okay. So I will take 0. So what is my approach? I mean, let's discuss, just quickly recap the approach. My tree has to be max tree because it has to be a max heap. Secondly, the tree has to be complete. Okay. So I will take 0. No issues there. Okay. In these type of problems, please make sure that you show all the steps. Okay. I will take 0. No issues there. Now the next step is that I am taking 14. Now if I take 0 and 14, it is a complete binary tree, right? But the problem is this is not a max tree, so I cannot call it as a max heap. So what do? I swap the nodes. Now if you see my third subtree, my third tree which is shown on the screen, it is a complete binary tree and parent is bigger than the child. Now some of you are asking like what is complete binary tree? I'll just mention it once again. All the levels should be completely filled. So level 1 maximum nodes 1 possible which is there. Level 2 except the last level, and the last level in this tree is 2, which is exceptionally permitted. Last level is permitted, but whatever nodes are present, they should start filling the tree from left side onwards. So 0 is on the left side of B, which is acceptable. So this is a complete binary tree. Okay. So some of you are asking me to explain again. So please, I cannot go over and over again over the same thing. Please review the last week's video and the slides. Now, what is the next node? Next node is -4. Where shall I keep -4? Right. So some of you answered it correct. I need to see one discipline which I need to follow is that I cannot afford to insert a node in such a way that the resulting tree is not complete, right? So -4, I need to put it in as a right child of 14. So if you see like the tree is complete, right? Property is still maintained. And if you see max, this is a max tree also. It's a complete, it is max tree, so it is a max heap, right? Now next node is 87. So where do I need to insert 87? What is your thought? Right. So you are answering it right, several of you. 87 should be the left of 0. Why is it so? Because the property of completeness is maintained. Tree is complete, but the problem is it is not a max tree because 0 is smaller than 87. So what do? I swap 0 and 87 values are swapped. Is it a max tree now? No, because 14 is smaller than 87. So I will do a swap again. So the last tree which you see on the bottom, 87 is the root with 2 children 14 and -4, and 14 has one child 0. This is a complete tree, right? This is a max tree, right? So this is a max heap. All right. Now last node is 86. So I would insert it as a right child of 14. Why is it so? Because I need to maintain the tree as complete. I cannot violate that property. But when I do it, when I insert 86 as a right child of 14, my max property is gone. So what do? I will swap 86 and 14 And the final tree, if you see, it is a complete also, and it is max tree also. So this is the final maximum. So if you are asked a question like this in the mid-sem exam, this is what is expected. Okay. Now, after constructing the tree, I can ask you to perform traversals. I can ask you several other things over this tree. Again, there is an exercise given here. Okay. So you have to construct a tree taking one integer at a time from left to right. You have to perform traversals. You have to store it in an array. So many operations can be done over here. So I am moving to the next topic, which is binary search tree. But before that, let's take a break for 5 minutes.